So I'm going to talk about anti-de Sitter geometry and polyhedra inscribed in quadrics. And this is joint work with Jeff Danciger and Sara Maloni. And I saw that, in the title of this conference, there is the term synthetic geometry. So actually, I'm going to be talking on synthetic geometry, which is, not so common today. I should say this talk is going to be similar to the talk by Juan Soto yesterday, in the sense that I have the same ugly viruses that he had and that he still has. So maybe it's going to be a bit tough to talk, but otherwise, the subject, mathematically, it will not be the same thing. Right, so, okay, so what is synthetic geometry? I mean, this guy is considered to be one of the top synthetic geometers of history. His name is Jakob Steiner. He was a Swiss mathematician living in the beginning of the 19th century. And he studied the combinatorics of polyhedra and the relation between the geometry of polyhedra and their combinatorics, which was somehow a new subject at the time, because before that people had been studying regular polyhedra a lot, but what Steiner got interested in was studying any polyhedra, not necessarily regular polyhedra, with more complicated combinatorics and so on. And he introduced a number of questions, especially in this book, which was his main work, maybe, published in 1832. For instance, he asked the following questions. What are the possible combinatorics of polyhedra? Polyhedra meaning, in this talk, convex polyhedra in Euclidean free space or in projective space, because those questions are mainly projectively invariant questions. So this is a natural question, and it took maybe a little bit less than 1 century to be answered, and the answer was given by Ernst Steinitz in 1916. It's one of the main basic results in combinatorial geometry, and the answer is that the possible combinatorics are given by the free connected planar graphs. In other terms, if you take a graph in the two-sphere, which is the one skeleton of a cell decomposition, it can be realized as the combinatorics of some polyhedron in Euclidean space or in projective space. But actually, Steiner had a number of questions in this book, and he gave another question, which was question 77 out of something like 80 questions. And the question is the following. What are the possible combinatorics of polyhedra that can be inscribed in a sphere or in another quadric? Quadric meaning, again, a quadric in Euclidean space or in projective space. And so what does it mean to have something which is inscribed? Well, basically here, what we understand by inscribed is that the vertices have to be on the quadric, and the polyhedron has to be on one side of the quadric, which already, that's something you have to assume even in the case of the sphere. So I didn't draw a sphere, but that's very common. So you all know examples of polyhedra inscribed in a sphere. But you can also look at polyhedra inscribed in this quadric, which I'm going to call H. It's a hyperboloid, and this one is a cylinder. I'm going to call it C. Okay. So if you think of it, this is really a projectively invariant question. So you're looking at quadrics in projective free space, and therefore there are only 3 quadrics, right? One quadric is a sphere, anything that is projectively equivalent to a sphere, like an ellipsoid. One is this hyperboloid, or anything that is projectively equivalent to it. And the third one is this degenerate quadric, which is a cylinder, with 2 points at infinity, where there are some singularities. Okay, so what do we know on this question? Well, basically, Steinitz worked on it too, and in 1927, he proved, the first result, which is that there are some polyhedra which cannot be inscribed in a sphere, right? Before that, it was not even clear, and those are, examples. Actually, there are simpler examples. I can draw a simple example for you if you want. This is a nice statement in elementary geometry. You can take a cube like this, and you can truncate a vertex. And a basic statement is that this, what did I do? Yes. This polyhedron cannot be inscribed in any quadric. And the reason is there is a elementary statement, which is quite interesting, that if you have a cube, a polyhedron which is combinatorially a cube, and 7 of the vertices are on some quadric, then the last vertex also has to be on the same quadric. So it follows from this statement that this cannot be inscribed in any quadric, in a sphere, hyperboloid, cylinder, anything. It doesn't work. Yeah. Anyway, so Steinitz found other examples. And now a better result, another result was obtained much later in 1993 by Craig Hodgson, Igor Rivin, and Warren Smith. I did not find a picture of Warren Smith, so sorry for him. I hope he's not in the room. And they gave a partial answer to Steiner's question. So they gave a criterion, which is a simple criterion in terms of solution of some linear equalities and inequalities. And I'm going to tell you later what this criterion is precisely. That tells you whether, if you have a graph, you can realize it as the combinatorics of a polyhedron inscribed in a sphere. So that's actually nice. It means that you can decide, if you have a graph, you can decide in polynomial time whether you can realize it as inscribed in a sphere or not. And the basic, the key idea that I'd like to give you is that the result is based on hyperbolic geometry and also specifically on the geometry of ideal hyperbolic polyhedra. Now, with those guys, so Jeff Danciger and Sara Maloni, we actually proved a couple of years ago this result, which gives us, in a way, a more complete result, an answer to Steiner's question. And the statement is simple, but we don't really understand it. I don't understand it. I can prove it, but I don't really understand it. So I don't really understand why this is true. And the statement is the following. So you take a graph in the sphere, which can be realized as some polyhedron. So it is, free connected. And the statement is that it can be realized as a polyhedron inscribed in the hyperboloid or in the cylinder. It doesn't matter. Both are, working the same way. If and only if it satisfies two properties. So one is that it is inscribable in a sphere, and the other one is that it admits a Hamiltonian cycle. Yeah, Hamiltonian cycle meaning a cycle, a closed path, following the edges and going exactly once through each vertex of the graph. Okay. So this is, for me this is not completely clear again why this should be true. It's pretty clear that if you can inscribe some graph gamma in a cylinder or in a hyperboloid, there has to be some Hamiltonian path. And I'm going to show you why this must be true. But I have no real idea why it is necessary that it can be inscribed in a sphere. If it can be inscribed in a hyperboloid, it can be inscribed in a sphere. And this is not clear. Again, I'm going to try to tell you how we can prove it, but it doesn't mean we understand why this is true. Yeah, okay. So now I'm going to go to chalk, and I'm going to give you the idea of the proof. And then I'm going to give you details on some parts of the proof. So basically, how do you prove the Rivin-Hodgson-Smith theorem? So Rivin-Hodgson-Smith, this is proved through a description of, okay, let's write it, a description of dihedral angles of ideal polyhedra, ideal hyperbolic polyhedra. By the way, can everybody read what I'm writing on the blackboard? Yeah? Okay. Yeah. The second idea is that polyhedra inscribed in a hyperboloid or in a cylinder, well, they have some interpretation in terms of anti-de Sitter, so they correspond to ideal polyhedra in what we call ADS3. And ADS3 is some analog of hyperbolic geometry of the hyperbolic space, but it's a Lorentzian analog. It's called the anti-de Sitter space. And I'm going to explain what it is. And this is for H. And for C, it's going to be something else, which I'm not going to talk about much because I won't have much time. It's going to be HP3, which is called half-pipe geometry. hyperbolic. And this was basically introduced by Jeff Danciger in his thesis a few years ago. So, and then what we're going to do is we're going to describe their dihedral angles. And there is a notion of dihedral angle for those ideal polyhedra, and we can describe exactly what the dihedral angles are, similarly to the description given for ideal hyperbolic polyhedra. Now the third thing that we're going to do is the the two statements, and this is going statements. Oh wow, statements. This is going to lead to the proof of this theorem, and this theorem that I have here, I'm going to call it Theorem A. Yeah. And the third point that I'd like to stress out is that it looks like we do the same thing in ADS3 as what is done in hyperbolic space, and the point is that this doesn't really work in that way because the proofs have to be done in completely different ways. And the reason is that the key tool that makes things work in hyperbolic space, this key tool does not work in ADS or in anti-de Sitter space. Sorry. Okay. Yeah, good. I'm going to remove the screen in a moment, but I still would like to use it for a time. So the idea is that proofs are different. Okay. Any questions on this? So let's talk a bit about polyhedra inscribed in a sphere. I'm going to explain the result by Rivin and his collaborators. So in a sphere. Whoops. So what is the key idea here? Well, you have this. I'm not going to explain hyperbolic geometry to you. I guess you all know what hyperbolic geometry is, I hope. And what I'm going to do is remind you that there is this Klein model, which is also called the projective model of hyperbolic space. And when you use this model, you can look at a polyhedron inscribed in a sphere. I'm going to do some completely idiotic drawing in 2D because I don't know how to draw things in 3D. And if I interpret, sorry, if I interpret the ball as hyperbolic space, and this polyhedron becomes an ideal hyperbolic polyhedron. Yeah. So this first idea, which goes back to Smith, Rivin, and Hudson, is that polyhedra inscribed in a sphere correspond to ideal hyperbolic polyhedra. So we have the following theorem, which I'm going to call Theorem B, and it's due to Andreev in 1970 and Rivin in 1992, I think. I'm not completely sure about the precise dates. So Andreev proved it for polyhedra with acute angles, and Rivin gave a proof for any angle, so angle going from 0 to 2 pi. And the statement is the following. So I consider a graph gamma in S2, which is, admissible. So it's the one skeleton of a cell decomposition. So this is my polyhedron, and I want to know whether this can be realized as combinatorics, so one skeleton of some polyhedron inscribed in the sphere, or in other terms, some ideal hyperbolic polyhedron, with given angles, dihedral angles on the edges. So for this, I'm going to choose a function w from gamma 1. So gamma 1 for me is the set of edges of gamma, right? So it's going from gamma 1 to 0 pi. Yeah. Then the statement is that W describes the exterior angles. So those are the usual dihedral angles, but you take pi minus the usual angles. So the exterior angles of some ideal polyhedron oops, if and only if two conditions are satisfied. So one is that for every vertex V in gamma 0, so gamma 0 is the set of vertices of gamma, then I look at the sum for every edge containing V of W of E, and this must be equal to 2 pi, right? So this is for elementary reasons. Basically, you know, when you have a polyhedron like this, you can look at the link, which is the intersection with some small horosphere centered at the vertex. And what you get in this link, this is a Euclidean polygon. And from this, it's easy to see that this sum has to be equal to 2 pi. So that's my first condition. It's quite obvious that it must hold. But there is another condition which is a little bit less obvious, which is that for any other path C in gamma star, I'm going to explain what this means. The sum for E in C, of W of E is bigger than 2 pi. So what does it mean? Now, basically, when I have a graph, there is a notion of dual graph. I'm going to draw this very quickly. And the dual graph has edges corresponding to the edges of gamma, has vertices corresponding to the faces of gamma, and it has faces corresponding to the vertices of gamma. So the way this works is the following. So this is my original graph. Let's draw something like this. It doesn't matter much. And the dual graph works in the following way. Oops, sorry. I should think of... So the dual graph works in the following way. Oops. This is going too fast, sorry. Yeah. The vertices are associated to the... So this is a combinatorial construction. So the vertices are associated to the faces of gamma. And then there are edges corresponding to edges of gamma. And therefore, it's easy to see that the faces of gamma star are corresponding to the vertices of gamma. Yeah? And so from this, you understand what it means to take a path in gamma star. And what I mean by other paths is, of course, there are some passes which are already occurring in the first condition. And those are the passes corresponding to the boundary of a face of gamma. If you take something going around, of gamma star, if you take something going around a face of gamma star, this corresponds to taking all the edges arriving at V. So this is something we already saw, and we don't want to have those passes because otherwise the sum has to be 2 pi. We already know this. Okay? Now, from this, you obtain the condition that was given by Hodgson, Rivin, and Smith. And what is the condition? Basically, if you take a graph and you want to know whether it can be inscribed in a sphere, basically you just look at the conditions which are given by those two. The equality and inequalities given by those two conditions. And if there is some solution to this system of equations and inequalities, then you can inscribe your graph in the sphere, right? Simply because you can realize the function, you have some angle function that you can get as the angles of some ideal polyhedron with the right combinatorics, and therefore you have solved your problem of inscribability. Yeah? Sorry. Yeah. Sorry. Yes, you're right. It's a closed path. It's a cycle. So it's another closed path. Thanks a lot. Yes. Thank you. Good point. And I'd like to say something about another statement, also proved, but in a slightly different way by Rivin. So I'm going to call this Theorem C. And it's a sort of dual statement to this new statement on the possible angles of some ideal polyhedron. And basically, you can think of ideal polyhedra in two ways. You can look at the angles at the edges, or you can look at some metric data on the boundary of the polyhedron. And this could be in terms of length of edges, although it's not completely obvious to define, or shear at the edges, because when you have two ideal triangles meeting at an edge, you can define their shear. Probably know this. But anyway, you can think of it in terms of induced metric on the boundary. And the statement that Rivin gave is a description of the possible induced metric on the boundary of ideal polyhedra. And I'd like to state it in the following way. So I'm going to take M, hyperbolic, a complete hyperbolic metric. I'm not going to write it. A complete hyperbolic metric of finite area, so with cusps, on S2 minus P1 up to Pn. I'm removing some points, and you need to remove at least 3 points. Then there exists a unique ideal polyhedron in H3 such that the induced metric on the boundary is isometric to M. Yeah, I should say this up to isotropy, but let's forget about those details. Okay. So now what I would like to say is that there is a way to do the same sort of things in ADS geometry. And I'd like to explain what ADS geometry is, and then we're going to see how this can be used to prove the theorem, Theorem A. So what is ADS geometry? Well, first, we need to define the ADS space, and ADS is defined mostly as hyperbolic space. There is only one tiny difference. So ADS3 can be defined as a space of vectors Rx in R22 such that x is equal to -1. And here R22, this is simply R4 with scalar product which is of signature 2, 2. So dx squared plus dy squared minus dt squared minus dt squared. Yeah? So, if you wanted to have hyperbolic free space, you would have R31. That would be the only difference. This has constant curvature. So, I should say this. It's a Lorentzian space. It's the metric at each point has signature 2, 1. I mean, 2 positive direction, 1 negative direction. So it has constant curvature -1, and the fundamental group of ADS3 is equal to Z. Yeah. It has a projective model, like the Klein model for hyperbolic space. Projective model, and the projective model is in a hyperboloid. So the projective model looks like this. So ADS3 is in this space. And what you see from this projective model, you see immediately that there are some nice features that you don't have in hyperbolic space, which are typically Lorentzian features. There are different types of edges, there are different types of lines, and different types of faces, right? So for instance, there are lines like this that do not intersect the quadric, right? So this is a line on which the metric is negative definite. So here we have what is called a timeline line. You have lines that intersect the quadric in 2 points, and those are space-like lines. The metric is positive definite, and you have lines that are tangent to the quadric at 1 point, and those are called like, and the metric is degenerate on those lines. So those are isotropic lines. And there is also a notion of totally geodesic plane. So because this has curvature -1, constant curvature, so they are totally geodesic planes. And those which look like this one, they are space-like, and the induced metric is isometric to the hyperbolic plane. Yeah. So you immediately see that this has connections to hyperbolic geometry in 2D, and this is something that's going to not appear much in my talk, but I should say a word about it, because this is the main motivation for me for studying ADS geometry. So let me give you some motivations. There has been quite a number of works on ADS geometry recently. And basically the point is that there are strong connections between ADS geometry in 3D and Teichmann theory, or hyperbolic surfaces. Like there is a strong connection between hyperbolic geometry in 3D and Teichmann theory, coming from the Beer's double uniformization theorem and so on. So one thing I should say is that the isometry group of ADS3 is very interesting for us geometers. I mean, clearly, by definition, it is O22, right? By definition, it is the space of linear isometries acting on R22. So it is O22. But up to finite cover, this can be decomposed as O21 cross O21, and it can be written also as PSL2R. So this is up to finite index cross PSL2R. And there is another way to write it, which is very interesting for us too. And you can write it as PSL2 of R plus tau R. And here, tau is, a variable such that tau squared is equal to 1. So this, is very close to what we have in hyperbolic geometry in 3D, where we have PSL2C, and C is R plus IR, where I squared is equal to -1. In this case, we have this tau R. And this is going to come up in the end of the talk, hopefully, if I have time. So then there are connections to, let's say, Teichmann theory or hyperbolic surfaces. And this comes up in the work, this appeared in the work of Mess in 1990. And so Mess proved two things. He proved an analog of the Beer's double uniformization. And I'm not going to tell you exactly what his statement is, but he connected this to earthquakes on hyperbolic surfaces. And he basically gave a nice proof, and a very simple proof of Thurston's earthquake theorem. Thurston's earthquake theorem. So that's, there was a proof provided earlier by Kirchhoff using analytic ideas. But the point is that if you understand, ADS geometry, you have a very simple and very natural proof. And this is what Mess found. Yeah, so those are some motivations from the 90s. And actually, there are lots of recent work. I should mention a few people just for their names. I'm not going to quote any results. So the result by Barbeau. Let me get a list. Francesco Bonsante, Jeff Danciger, Fanny Cassel, François Guérito, Gabriele Mondello, and a number of other people. I'm not going to try to quote everybody, but the idea is that there are a number of people working on ADS geometry now because of the connections to Teichmann theory and to hyperbolic surfaces, and using this geometry you can find results on Teichmann theory and hyperbolic surfaces. Yes?
So is tau not equal to -1?
Excuse me?
It's not,
I didn't get it.
Tau is not -1.
No, tau is equal to 1. So this is, basically R plus tau R. This is something that has been used a number of times. If it was -1, it would be complex numbers. And those are, called...
No, I'm not talking about tau square. I'm asking about tau.
Tau. No, tau is a formal variable. Right? Like I, when you want to define complex numbers, how do you do this? You take some formal variable I,
right,
and you define it, in such a way that I squared is equal to -1, and you take the set of, of numbers of the form R plus tau plus IR. And here you do the same, and you find things that are called complex numbers, almost complex numbers, or Lorentz numbers, or double numbers. I mean, there are not many names. But it basically, if you look at it in this way, you can identify the isometry group of ADS3 with this PSL2 of R plus tau R. And the other things, I'd like to, if I have time, I'd like to show you at the end of the talk another situation where you can do something that is very analogous to what you do in complex geometry with C replaced with tau plus R plus tau R. And you actually prove a theorem using this. Okay. Okay, so let me try to show you ideal polyhedra in ADS3. So those are, those will be what they look like. So ideal polyhedra in this case, they will have vertices at infinity. And you sort of visualize this because the vertices correspond to the intersection of two lines that foliate this quadric. And so what you know by definition is that the edges, we said that the space-like edges are the edges that intersect the quadric in 2 points. So by definition, it's clear that the edges that you'll have are space-like edges. And you can prove fairly easily that the faces of those polyhedra, they have to be space-like faces. So they are isometric to a piece of the hyperbolic plane. So what you also see is that there is some new notion that doesn't appear in hyperbolic space. Namely, there is a notion of time direction in this space. We can take a time orientation. If you move in this direction, you go to the future. And if you go in this direction, you go to the past. And now if you look at this polyhedron, there is a notion of a past region and a future region. So the past region is in the bottom, and the future region is in the top. And if you look at this, the red edges are the edges separating the the future boundary from the past boundary. So what you have in this situation, again, is this disk, which is the future boundary, the other disk on the lower side, which is the past boundary, and the two are glued along some cycle that is this red cycle in this picture. And also by definition, this cycle has to go through every vertex. So you already see from this construction that you have this Hamiltonian cycle that is necessarily there. Whenever you look at the combinatorics of some ideal hyperbolic polyhedron, you need to have some Hamiltonian cycle. Yeah? Is this clear? Okay. So maybe I should get rid of this now, if nobody objects. Up. Press again. No, that's okay. And I'm going to give you some theorems on the possible angles of ideal hyperbolic polyhedra. First, I need to define what the angles are. Basically, what are the angles? It's not completely obvious what we call the angles. So how do you define the angles of some polyhedron, dihedral angles of some polyhedron in a hyperbolic space? Well, basically, you do the following usually. So you have those two faces meeting at two faces meeting at some edge, and then basically, you choose some plane which is orthogonal to the face, right? And it's intersecting here. It is orthogonal to this edge, and then basically you look at things in this plane, and what you see in this plane is two lines intersecting in this way. And basically, the point where you put this plane doesn't matter. You'll always get the same picture. And then what you do is you take the normals to this line and to this line. You take the scalar product, and you define the angle to be theta, such that the cos of theta is the scalar product. And here you're going to do the same, but now we are in ADS3. So basically, if you're in this situation, there is this Lorentzian normal N1 here, and then there is this Lorentzian normal N2 here. And you define the angle, which is theta, such that the cosh of theta, maybe minus the cosh of theta, is the scalar product of N1 and N2. And this plane can be considered as the ADS2 plane, or it can be actually, this is local at the intersection, so you can do this in Minkowski space, in the Minkowski plane. Yeah? So this is the notion of angle that you want to consider on those edges, right? But actually, there are two types of edges. because of what we saw earlier. Basically, you know, this is what happens if you are in some edge within the future disk in this polyhedron. But often what you'll see is something different. What you'll see in some cases is you have a face of the future disk and a face of the past disk. And the edge that you want to consider is the edge which is separating the future from the past disk. And in this case, what you do is you have this Lorentzian angle N1, you have this Lorentzian angle N2, and then you have a slightly different definition. You know, here, actually it's going to be the same formula, but in this case, for some reason, we want to take theta positive, and here we take theta negative, and you define it such that the cosh of theta is equal to minus N1 scalar N2. So I don't want to explain why this is a natural definition, but it turns out this is what we need for what we want to do. Okay? Now from this I can state a theorem, and I'm going to call it theorem B prime by comparison with B, which was the theorem of Andreev and Rivin. So B prime is the following. So this is something we proved with Jeff and Sara. So we take again gamma in S2, and we suppose it is the one skeleton of cell decomposition. And then I'm going to take a function W from the space of edges of gamma, gamma 1, into R, but I don't want those angles to be equal to 0, right? This wouldn't make sense for me. So I want to take it with values in R, not 0. And then I'm claiming that W describes the angles defined as here of an ideal ADS polyhedron if and only if two conditions are satisfied. Three conditions are satisfied, sorry, yes. The first condition is that W of E is strictly less than 0, exactly on the edges of a Hamiltonian cycle let's say gamma, in big gamma. Yep. So this is the first condition. Basically, we saw earlier why this has to be satisfied, because this is happening on the Hamiltonian cycle, which separates the past disk from the future disk. Now, the second condition is exactly as in the Rivin-Hudson theorem here, Rivin theorem here. So for every V which is in the space of vertices of gamma, I can take the sum over V contained in E of W of E, and this has to be equal to 0. There's a small difference with the hyperbolic situation. This is not 2 pi but 0. And the third condition is that for every other cycle C in gamma star, and I have to add some condition. I don't really know why either, but anyway, I want this to intersect gamma. So gamma is this Hamiltonian cycle exactly twice, 2 times. Well, then I have that the sum over E in gamma, in C of W of E is strictly positive. Yeah? So except for those tiny differences, this is almost the same statement. And by the way, I'd like to state another theorem, which is going to be proved together. So it's the analog of theorem C, but in this ADS setting. So it's also proved with Sara, Maloni, and Jeff Danciger. So the statement is that if M is a complete, a hyperbolic metric with cusps of on S2 minus a certain number of points, P1 up to Pn, with n at least equal to 3. And let gamma be a Hamiltonian path in in S2. So, well, what I mean by this is I take a path going through all the PIs exactly once, and I want to consider it up to isotopy fixing the endpoints. Yeah, fixing the marked points, right? So you want to know where this path goes, if it goes to the left or to the right of a given PI. And then there exists a unique P in ADS3, which is an ideal polyhedron. Uniqueness is up to global isometry, of course, such that the induced metric on the boundary of P is M, and this, this cycle that separates the path and the boundary disk, I'm going to call it the equator of P is isotopic to gamma. Yeah? So that's the statement. Again, it's the analog of the Rivin theorem, but in this setting where we have to add this topological data. Okay, so from this we can prove Theorem A. So how are we going to prove Theorem A? Well, the idea is very simple. Maybe I should repeat Theorem A. So Theorem A, I'm going to rewrite it. So gamma, as previously, so the one skeleton of a cell decomposition of sphere can be inscribed in H. So this is my hyperboloid, respectively P, which source C, which is my cylinder, if and only if two conditions are satisfied. So it has a Hamiltonian cycle. And two, it can be inscribed in the sphere. Yeah? So how do we prove this? I'm going to explain the proof in one case and in one direction. So I'm going to choose the case of EDS because meaning of H. So I'm going to give the idea of the proof in H, for the case of H, right? So what can I do? So I'm going to suppose, it's going to work basically the same way in the other direction. I'm going to suppose that H, I'm sorry, that gamma can be realized as the one skeleton of a polyhedron inscribed in H. I'm going to write this as can be inscribed in H. So what do you get from theorem B prime? Yeah, you look at the angles. So we have a function W from gamma 1 to R different from 0, satisfying those two conditions. Where are they? The conditions there, right? So there is this Hamiltonian cycle, and this, already. Sorry. No. So you have this Hamiltonian cycle where the values of W are negative, and the values are positive on the other side. So, but the problem is that the values could be bigger than pi, right? There is no reason why they should be between 0 and pi, or between minus pi and 0. So I'm going to choose T positive such that TW of E is between minus pi and pi for all E in the set of edges of gamma. Yeah? And OK, now I get something closer to what I need to be able to apply theorem B. My goal is to apply theorem B to find a way to inscribe this polyhedron in a sphere. But it's better because now most values are between 0 and pi, but some of them are between minus pi and 0. So I have to add something. on the negative edges. So I'm going to define gamma prime, w prime, sorry, from gamma 1 to 0 pi in the following way. W prime is equal to w if w of E is positive, and it's equal to w of E plus pi if w of E is negative. Yeah, that's a fairly natural choice. Now, what I should remark is that, if you look at any edge of this polyhedron, there are exactly two red edges arriving at that edge, right? Because, there is this, positive, the future disk and the past disk, and there are exactly two edges separating the two. So then what I immediately see is that for every vertex of gamma, for every v, the sum for v in E of w prime of E is equal to 0 for every v in gamma 0. Yeah, so that's the first condition. Now, there is some other condition. If I take any path, closed path in gamma star, so C be a closed path in gamma star, and if I suppose that it intersects gamma twice, so gamma is this equator, the set of edges where the path of edges where all the values of w are negative, then the sum over E in C of w prime of E, this is, well, actually it's 2 pi because you have exactly two intersections. So you'll be adding pi in exactly two edges, and this will be plus the sum over all the edges in C of T w of E, right? And we know by definition that this is positive, so this is going to be bigger than 2 pi. So in this case, we have that the second condition in theorem B is satisfied. And well, the point is that there is this condition, the gamma intersects this path twice, this path gamma twice. And the point is that if you have another closed path intersecting more than twice, well, basically you will be adding 2 pi more than once, and you'll have 2 pi plus something else, and maybe there's going to be some problem, but it's also it also works even more easily actually for other paths. And I just have to add that if T is small enough, right? Basically, the idea is that if you have another path, maybe this is not going to be positive. It could be less than 0. But because you're adding 2 pi more than once, you'll end up something which is still positive for any bigger to 2 pi, sorry, for any path, right? I think this should be reasonably clear. Okay? And then now you can apply theorem B, which is an array of Revin result, and you obtain that gamma can be inscribed in S. Yeah? Simple. And basically the idea is that the converse works the same way. It's more or less, well, similar, I should say. And for the cylinder, it is not the same. You have to use, so the cylinder, you have to use, instead of ADS3, you have to use this space HP3, which is the half-path space, which was introduced and worked on by Jeff Danciger in his thesis. Yeah? So this is the proof of theorem A. Do you have any questions on this? No? Good. So now I'm going to give a hint maybe of the proof of theorem B. And actually, the theorem B and theorem C are proved at the same time. There are reasons why it's important to look at the two things at the same time, because the key part of the proof is going to be, proved together basically in the two settings, for the induced matrix and for the dihedral angles. Okay. So what are the key ideas of theorem B and C, B prime and C prime, sorry. So the point is that it's not the same as for theorem B. So how do you prove theorem B? Basically, there is a nice way to prove it, which was worked out by Revin. And it is based on a very interesting and very powerful fact of hyperbolic geometry. And this fact is that if you take the volume of an ideal hyperbolic simplex in 3D, this is a strictly concave function of the dihedral angles. This is something that should come up in the talk by Fang in the next talk, I guess. Right? And the reason we cannot apply this is that this is not true in ADS. So the key point is that the volume of an ideal simplex in ADS3 is not a concave function or a convex function of the dihedral angles. And this means we have to use completely different arguments. So what do we use? Basically, we're going to have several inputs. So the key inputs are the following. So one thing is that we're going to use some, basically classical geometry. By classical, I mean basically geometry from the Russian school in the 50s or 60s, maybe. And specifically, we use ideas of, Pogorelov for the rigidity of polyhedra. Actually, this came up in the previous talk. That's funny. Same person, but I mean, almost the same type of mathematics. Another thing that we actually use a lot are ideas, not results, but ideas from quasi-function manifolds. And basically, mostly quasi-function manifolds near the function locus. And the people we need to quote here are Bonaon and Series, basically. So basically, there are some results from Bonaon and Francis Bonaon and Caroline Series that are very close to what we need in this polyhedral setting. And we use those ideas, although we don't use their results, we use the same type of ideas. And the third input is this notion of transitional geometry. Which is something worked out by Jeff Danciger and Steve Karkoff. And the idea here is that you have this ADS geometry here, you have hyperbolic geometry here, and basically there is a way to look at half-pipe geometry as some intermediate geometry between ADS and H3. I didn't tell you what half-pipe geometry is, and I don't really want to talk about it, but half-pipe geometry, it's a sort of constant curvature degenerate geometry. Degenerate meaning that the metric that you look at is a metric which has a degenerate signature. So it's positive in some directions, but it is isotropic in other directions. Okay. Any questions on this? Maybe I'm going to tell you a bit more. I don't have time to tell you a lot about this, but I'm going to tell you how the proof proceeds. And the general idea is that it's a very classical way of looking at things. So we take, n at least 3 points on S2. And basically, first I'm going to explain the proof of theorem C, and then theorem B. It's a bit more intricate. So, we look at the space P gamma. Oh, sorry. I need to take gamma a Hamiltonian path, going through those points. Cycle. Yeah. So P gamma is going to be the space of ideal polyhedra with vertices. So ideal polyhedra in ADS with vertices identified with the marked points up to global isometry with equator. With equator. So equator meaning again the cycle separating the past disk from the future disk. equator gamma. Then we have space tau gamma, which is the space of hyperbolic matrix, complete hyperbolic matrix on the spheres with cusps at the marked points up to isotopy. And then there is a natural map from phi gamma, from p gamma into tau gamma, which is the map sending some polyhedron to the induced metric on the boundary, right? Very natural thing to do. And basically, we want to prove that this is a homeomorphism. So basically, if you can prove that phi gamma is a homeomorphism, then we win. We prove theorem C. Yeah? And for theorem B, basically it works the same way. So now we have P gamma and big gamma. So it's the same definition here, but now we fix the combinatorics. Yeah? So ideal polyhedra, ideal P in alias 3 with combinatorics gamma and equator given by small gamma up to global isometry. I have this space of angles, possible angles. So this is my space big A, small gamma, big gamma. So this is a space of functions defined on the edges of big gamma into R, taking non-zero values. And those are what I like to call admissible metrics. Admissible functions. And then I have a map psi, small gamma, big gamma that takes P, small gamma, big gamma, to A, small gamma, big gamma, sends some ideal polyhedron to the values of its dihedral angles, right? That's a pretty natural definition, way to proceed. Now, again, if I prove that this is a homeomorphism, then I have proved theorem B. Now, the difference is that you fix the combinatorics. That's a small difference. So how do you prove this? This fact that phi gamma or psi, small gamma, big gamma are homeomorphisms? Well, there is a key point, and then there is some technique. And I'm coming close to the end of my time, so I'm just going to give some ideas. So why is phi gamma a homeomorphism? So the first thing you have to prove is that at each point, the differential of phi gamma, so this is a map, you can prove that it's a map between two spaces of finite dimension and the dimension is the same. So you can look at the differential of this map, which happens to be differentiable, and it is an isomorphism at each point. So what does this mean? It means that if you take the polyhedron, you move the polyhedron a bit, you're going to change the induced metric a bit. And this means precisely that it's the statement of infinitesimal rigidity. Yeah, with respect to the induced metric. Now, the second thing you have to prove, and this is some maybe more technical aspect, you have to prove that phi gamma is proper. And you have something which is, basically if you know that the differential is an isomorphism, you know that this phi is a local homeomorphism. If it is proper, then you know it's a covering map. And then you can conclude by some topological arguments, which is basically that P gamma is contractible. Well, that's connected, sorry. It's connected. And that the space of metrics is connected and one connected. Right? If you have this, then you can conclude. And this is for proving that phi gamma is a homeomorphism. And for psi gamma, you have a small difference. So this is for psi gamma gamma. The difference is that now you prove the same first steps basically, and you're going to use that psi gamma, small gamma, big gamma is a homomorphism near, okay, for let's say almost flat polyhedra, which means basically you take small angles. Okay, so maybe I'm going to say one thing very quickly about how we prove the first point. So the first point for this map, phi, it's proved using classical geometry. So basically you know that Euclidean polyhedra, convex Euclidean polyhedra are rigid. This is a statement proved by Cauchy, Legendre 200 years ago. You know that they're also infinitesimally rigid, meaning if you change them a bit, you're going to change the length of the edges. And this is something that was proved by Dane 1 century ago, 1916. And then actually something more subtle that was proved in the 50s by Alexandrov is that it's also, they are locally rigid with respect to the induced metric. So if you move them a bit, even changing the combinatorics, you have to change the induced metric. And then there is a trick invented by Pogoryelov that takes this rigidity statement from Euclidean space to hyperbolic space. And it turns out that this Pogoryelov trick works also in ADS. And if you use the ADS version of this trick, you actually proved that polyhedra in ADS, convex polyhedra in ADS, whether they're ideal or not, it doesn't matter, they're also infinitesimally rigid. So you cannot deform them without changing the induced metric. And this proves this statement for you. This is the key idea. And then if you want to prove the same thing for psi, small gamma, big gamma, then there is a trick due to Bonaron for quadrifunction manifold, basically. That is, for each, you can describe those polyhedra in terms of edge coordinates, of shape coordinates, invented by Thurston for ideal polyhedra in hyperbolic free space. But now, those shape parameters, they will be in this space R plus tau R. And basically what you prove is that if you have some deformation that doesn't change the induced metric, if you multiply by tau in this space of edge shape parameters, you'll find a deformation that does not change the dihedral angles, and conversely. And this is how you go from the rigidity for this theorem C to the rigidity for theorem B. And the rest of the proof, I mean, there are some work to do, but basically, there are some technical things. So I'm going to stop here, and I'd like to thank you for your attention.